I can try this again. I will try to do it in less than 45 minutes so I can show you like basically what I was explaining before. Let me get back to the project. Basically, I was going to explain the AMIDI library code that we have been looking at in the Rust Audio Basics repository. The AMIDI library code that I wrote shows how you can write type defs to map to symbols in a shared object. So like it sounded like you were slightly confused about how that works. So I'm going to show that to you now so you can see how you can write a Rust abstraction over a library interface. When you do that, what basically happens is that there are a set of symbols in this shared object. When you can access one of those symbols with the get call on the libloading library type. Yeah, this is already going faster because it took me like, wait, hold on. Rust Audio Basics. Oh shit, my computer is slow right now because I'm running a model of something. So I hope this works and it isn't too laggy. I need to replace the machine. I I chose a 1 terabyte size hard drive for this machine. Is just not enough. So I always need to like clear space and always get more than a terabyte. This AMIDI library is what we're looking at. Basically here, which you can see at the top, the first item in the structure is called library. This is a arc wrapper around the libloading library type. Libloading library is what you use for loading a .so file and accessing the symbols in it. The way you access a symbol is actually just by the byte string for its name. So down here, you can see that what we're doing is we're first loading the shared library at the path that we found earlier. We load that library. This is like one of the types from libloading. If you want to see how that works, run a cargo vendor in your repository and then go to vendor libloading and then source safe. Okay, so here is the loaded dynamic library. This is a really simple interface. It literally just has these doc comments are pretty useful to read in case you want to know how they work, but it just has new and it has get and close. So when you close it, you like just that closes the library. When you run new, that loads the library into memory. And when you run get, what you're doing essentially is you're giving it a byte string for the symbol name. The library is full of symbols. They have specific names and you need to know them in advance in order to access them. You can see them with like a shared object dump or like nm or different commands like this can show you which symbols are in your library. We're looking at like the MIDI library here. We have it loaded. So like when we run this, I'm not sure exactly which code we're. Yeah, so like libamidi.so, that's our shared object file. When we load it, we use that to create one of these structures. And like I created this structure from scratch. There's not like a blueprint for how to do this. I mean, you can put anything you want in your structures. This is just like a useful abstraction that can help organize a software system like the one you're creating. What we do here is inside of our shared object, we have a set of, obviously the symbols. The symbols are like, it's like they lead to function pointers. So if you know the interface for your function, you know the signature, you know the symbol name, and you have the library, you can use the symbol name with a pointer to the library to access the function pointer, which you can then use to call the function. That's how it works under the hood. But you need to know what the function signature is, because otherwise you can't pass the arguments to the function. Like when you're, like language is aside, if you think about like what all languages are doing, you're when you call a function, there's some assembly code, right? That runs, and it basically transfers you into the context of the function, and then runs the set of statements in the function, and then transfers the result back to the caller. Basically, it's like some assembly instructions. So this is what, if you go low enough, this is what's happening under all languages, because it's all just running machine instructions. All of your languages at the end, all they're doing is they're sequencing. When they compile, they're just sequencing the sequence of assembly instructions that the machine needs to run, right? So when you run a function, what you need is the pointer to the function, like the address of the function definition inside the shared object file. You need that, and then you need they're like addresses of where all of the function arguments are stored. And depending on which function arguments you have, it looks slightly different, but that's what the languages are all designed to handle. And this is why it's actually possible to seamlessly interface between languages. But making sure these wrappers are in place properly is what allows that to feel like it's transparent to you as a programmer. So what we do here is we basically load the library using libloading. This is, as far as I remember, this was working successfully in the example that we've been collaborating on. Here, you're giving the get call on libloading library, you're giving the get call a byte string, which represents the symbol. What's happening is that you're using this symbol to access the function that the symbol leads to. And you're using these type defs to alias the signature of that function such that you can work with them fluently in Rust. That's all this is. All this is this is saying, it's like pre-coding in knowledge of, we know which symbols are in our shared object. We know which symbols are in our library. We know what their interfaces are because we have knowledge of how that shared library was compiled in C or C++ or whatever it is. We know which symbols, we know what their signatures are. So we can create type defs that are unsafe and they're extern C, but this is essentially the type of function pointer that you're gonna get if you access the symbol from the shared object. So this is like a long-winded way of explaining what all this code is doing. All this is, everything in this file is just type defs, which say the symbol, we know that a symbol with this signature exists. We're gonna call anything, a function pointer of this signature, a certain type. That's why we can do type safe. We can do this particular call in a type safe fashion, because what happens is libarc.get of the byte string, it produces a function pointer, right? Which we're saying is the same as this type. So then what we're doing is we're storing all of the function pointers that we calculate inside this AMIDI library structure. So by the time this new function ends, you've essentially initialized all of the function pointers that you need from the shared object. They exist now as, they're like Rust types that you can then pass in parameters and call. So what that means is that down here in MIDI device and MIDI input port and MIDI output port, you can use the arc to the MIDI library, the AMIDI library, as like, it's like a conduit or something that you can then use to easily call the functions in your shared object from Rust. So what you do is you write, and I explained this in more depth in the other video, and like explaining all that again is going to be kind of I don't know if I'll be able to do it. it's mostly like what you're doing here is you're like writing Rust code that wraps that AMIDI library. And from that Rust code, notice here that once you create your MIDI device, you can call these functions on it, the ones that I'm highlighting. These are just Rust functions. But underneath the hood, what they're doing is they're accessing the function pointer found in the library, and then they're calling it with something that they uniquely have access to, or that they have access to. So these functions are now Rust functions. What it means is that, like, I'm just going to show you an example like of what this looks like in code. And I wish that this was going a little faster. My function, or my process here should already be finished, but it's not. I'm just going to show you what this looks like. The first thing you do is lib equals arc new a-midi. It's like this. So when you first run your program, what you do basically is the path to so equals know this up front. You might be able to use like an environment variable to configure this, or however you want to pass this into your program. You just have to get it into the program. But that path is the path to lib-a-midi.so. You're going to use that to initialize a MIDI library, which is this abstraction that we've been working on over here. You create one of these first, you wrap it in an arc, and then downstream, every time you create a device or an input port or an output port, so like let's say dev equals arc new MIDI device. I forget how you create this. It's like from Java, right? Lib dot clone and then env MIDI device. MIDI status D. Right. Yeah. Okay, so what this has done is it's created your device. What this means is you need to have env and MIDI device object in scope at the time you start this. So like let env is a mod jni env, right? I don't know exactly where you get this. This comes from somewhere. Right, and then you have let MIDI device object. This one is J object. This comes from somewhere as well. But when this runs, you now have a MIDI device, and this is an arc MIDI device, and this is an arc a MIDI library. And then you can do input ports equals, wait, what is this one? Input port equals arc MIDI input port equals arc new. I forget exactly how you do this. This is like kind of pseudocode, but I think you'll get the idea. Output ports. You need to have the lib.clone at least. I don't know what all the parameters for initialization of these ones will be, but you need to have the a MIDI library. The arc has to be cloned and passed into it. So like basically what I'm showing you here, but also syntax highlighting so you can see this a little better, is that as you create your program, you first start with the a MIDI library abstraction. What that does is, as we described earlier, it encapsulates the shared object file that you've loaded into memory, and it has the function pointers for all of the symbols that you need for your program already calculated. Then you pass that arc to the other abstractions that you end up creating, whether it's MIDI device, MIDI input port, MIDI output port. when you do that, those new structures they have a handle to talk to your AMIDI library. But at this point, you're totally in Rust world. You don't need to worry about the FFI because you've already encapsulated it. You've wrapped it, like if the FFI is here, you've wrapped it one layer out, and then you've wrapped it another layer out. And then once you've done that, you can make sure that everything inside this orb is totally safe and functional. The interface to all of that, though, you don't need to worry about FFI anymore at that point. So you can call the routines on input port, on output port, on device. At that point, you're just programming it however you want it to behave. You know, maybe you have like some loop where you're just like pulling some values. You're reading the values, you're using that to set parameters, and then you're writing out. Usually these programs just go like, at every instance of the loop, you're like reading the input parameters, the control surface, then you're writing the things internally, like you're writing the data internally that needs to be updated, like which pad is down, which pad is up. Like you're just writing the things that need to be written, and then you're like simulating one step. And like you're sending any audio buffers out to the audio thread, and you're just like, there's a basic pattern. I think it depends on what your system is going to do, but the main thing here that we're talking about is how you initialize everything. The reason why, I went into this in more detail in the other video, but the reason why you need the ARCs is that you don't want a MIDI library to be destroyed while MIDI device or MIDI input port or MIDI output port are using it. So you use ARCs in Rust to make sure that everything is atomically reference counted. And like when you create a MIDI library in the first place, the reference count goes to 1. When you clone it, it goes to 2. You clone it again, it goes to 3. You clone it again, it goes to 4. So by the time you get here, the ref count for lib is 4. At the end of the scope, the objects get destroyed in the reverse order. So like output port gets destroyed, the ref count for lib goes to 3. Input port gets destroyed, the ref count for lib goes to 2. Dev gets destroyed, the ref count for lib goes to 1, and then lib gets destroyed, and then you're back at, like, then the AMIDI library will be deinitialized. So I'm basically still explaining how this works here. You have the symbols, you can invoke the symbols are, by the time this structure has been created, all the symbols are initialized as the proper function pointers, and they have the right type signatures, which you define in here. If you want to add another symbol, that has a different type signature, you can add one here. There's no hard limit on this, and if you don't need some of them, you can take them out. It's not like your program will need it unless you need it. So if you find that there's another symbol, or you're looking at another library that you're going to use as a shared object and you want to work with that one too, then create another file. You know, maybe it's like libxyz library function pointer types, and you have libxyz's function pointer types in there. You have a MIDI library's function pointer types over there. You just have type devs for everything, so that way you can assemble Rust structures of them. This is creating like a basic set of abstractions that you can then use to, like, you basically want to quickly and efficiently and seamlessly and modularly get to the part where you're able to use the types as Rust types. And if you're calling this from Flutter, all of this should work just like the same way any other Rust code does. Because behind the scenes, these things are handling the foreign function interface. If you can create these types in a Rust program, and you can link from Flutter to that Rust program, you can use it. And then the Flutter code shouldn't need to know about how your AMIDI library or MIDI device or whatever are managing the symbols underneath. Your Flutter code should just talk to Rust. Your Rust should talk to the shared object. And then you don't even need to worry about like too much foreign function interface beyond that. As far as the Java environment integration, that's going to be another set of initialization activities that happen up here. You probably want to do that first. I think, yeah, you'll probably want to do that first, because, I mean, you could create the a MIDI library first, you could, and then you could initialize Java, and then you could do these. But you might just want to like initialize Java first, because then you're going to get the JNI environment, and like you have to be able to get these types to be correctly initialized too, because they're needed downstream when you initialize your MIDI device and MIDI input port, MIDI output port. So you have to get like the Java bridging layer done first, and then you can create these abstractions that I've shown you here. Yeah, I think that's like most. I went into like a more detail about how arcs work, the atomic reference count pointer in Rust, in the previous video. I don't think I have like the. It's gonna be hard for me to remember everything I said in it, so I don't want to try to butcher it. But basically, arcs are gonna be your best friend in this type of system, because it makes it so that it basically makes it so that objects are created and destroyed without, like, they hold references to each other. So you can create like essentially a tree of references. Like this is already a tree here. This code structure is already a tree, because MIDI device and MIDI input port, MIDI output port have pointers to lib. So as long as dev, input port, or output port are alive, lib will be alive. What it means is that you can, I don't want to get this too complicated. You can pass these around. You can use them as long as they're alive. Lib will be alive, because it has a clone of lib in it. I would say best advice would be like to not overthink it too much. Basically, no matter what program you write in this kind of space, it's going to look like the main function is going to be like initialize all the stuff. Once it's all initialized, you have a loop that you can then use the stuff, and that's going to be like when is the user is like interacting with your program. That's the loop. And as long as they want to stay alive, as long as they want to have the program stay alive, the loop will be running. It's interesting, like operating systems are designed to never start or end. They're designed to always be on. That's what lets the user be able to keep them on for as long as they want. There's certain routines that you can initiate that will start the shutdown process, and there's certain things that have to happen in order for it to reach that always on state, which are the initialization routines. But basically, no matter what kind of program it is, it's all going to be initialize everything, make sure everything is connected properly, get into the loop, do all the stuff you want to do for as long as you want to do it, and then when the user hits the quit command or whatever happens, you exit the loop, you cleanly tear down all of the objects that you've initialized that need to be teared down, which happens in drop, and then you exit the program. So that's what it'll look like basically no matter what. It sounds like, let me look at your question again. It's only for I'm not exactly sure. I haven't done Flutter, but I know it's kind of the same as everything. After a certain point, everything just becomes about the same as everything else. I know that sounds like weird, but every system that you're going to work with in a computer has like, there's some underlying principles that govern its behavior. And if you figure out what those are, then all of the interfaces over that, they're all kind of the same. So really, the main thing is you don't want to expose too much complexity, and you don't want to create triangles of complexity. It's better to have things not have too many moving parts. So everything that wraps a MIDI should be done from Rust. I think that's probably what it would be like. Wrap a MIDI totally from Rust. You already have the way to do that here. This is already going to work. Wrap it from Rust, and then from your Flutter side, just call that Rust. Initialize the Rust, then call it and work with it from the Flutter side. So when you need to call a Rust, function from Flutter, make sure everything on the Rust side that you need to have initialized is already initialized. Maintain a handle to the Rust, to the arc of whatever the Rust object is you need to work with that you can then call from Flutter. Don't worry about the foreign function interface from Flutter. Just call Rust from Flutter. Like, ideally, your Flutter code knows nothing about Java, and it knows nothing about a MIDI and the shared object implementation. Those are all implementation details. Your Flutter program should literally just see a Rust interface. Like, you can actually do it like this. You can just say, I'll write a new file, whole program. Like, let's just say program. I don't know. This thing will be your entire program. I think it's a sequencer. It sounded like it was either a sequencer or a drum machine. So sequencer. Inside here, we're gonna have the arc a MIDI library, and then dev is gonna be arc MIDI device, and we're gonna have input port is like MIDI input port, and output port is MIDI output port. And anything else you need to initialize. Like, there could be other structures here. I'm not exactly sure because I don't know what your whole architecture is, but like inside sequencer, you'll basically have every abstraction that you need to work with. When you create a sequencer, it's actually gonna be like this, probably, because you have when you create a sequencer, your job is basically to initialize everything inside of it one by one by one. So you could do this, and you could just say, let lib equals, this is where you initialize your lib, let dev equals initialize your dev, let input port output port, and so forth, and then you lib dev input port output port, etc. So from the Flutter side, if there's initialization code in Flutter, what you're essentially going to have there is you're going to have some Flutter that creates the sequencer and holds it. I'm not sure exactly how, it's probably about the same as other things, but I've seen some of the syntax. I don't know exactly where you initialize things in Flutter, but like let sequencer equals, it's gonna be like about as simple as you can get. You're gonna have this call somewhere. Let sequencer is sequencer.new, and inside that, all of these routines will run. So like, ignore this part for a second. Wait. Whoa. Ignore how you create this and ignore what's in it, because you don't really need that. What you do need to know is that in Flutter, you're going to create a sequencer, and then when you want to do stuff with the sequencer, you just call the functions on it. So like trigger pad, or like whatever the interface is that you want. Add notes, add clip, reverse sample, whatever you're doing here. Inside the sequencer, you have like a set of functions that you implement, and all of them talk to the underlying implementation pieces. You create one of the sequencers with this new call from Flutter, and then you have an interface, because you're going to have to implement all these functions, do stuff, right? You can get it as sophisticated as you want. whatever you have there, right? Your sequencer is what you implement. Underlying that, you maintain pointers to every low-level construct you need to create. And then from Flutter side, every Flutter UI call, like say there's a Flutter UI call for a certain button or for a certain drop-down menu for a certain checkbox or whatever it is. Inside those, your overall Flutter context will hold one of these sequencers. And so because it has that, from that UI call, you'll be able to call the method on sequencer that you need to achieve the desired goal. Even if inside you're creating it's like asynchronous, you could have it be asynchronous because all of these functions, in the end, you could use Tokio and you could have all of these functions be async. All of this could be async. There's nothing like against having all of these async, I don't think. I think that Flutter should probably do async calls, in which point you would do like await, or you just store them as futures. It depends on, you can trigger the call, store it as a future, and come back to it. There's like, at that point you're in Flutter world though, and all you really want to deal with is the interface. You probably, from Flutter side, you probably want to only have one Rust object that you're handling. That Rust object, you should be able to create it in a Rust program that knows nothing about Flutter and run it. So like you could have all your unit tests, all your tests, everything in Rust. You can write the thing in Rust. You should be able to run like test scripts that execute all the functions just from Rust. So you can be sure that your entire sequencer is correct without worrying about Flutter at all. All of this can be Tokio. I don't think there's any reason why you can't have Tokio in there. Then from the Flutter side, you just call the really simple interfaces. And if you want to have like, you know, in your sequencer, you have one region of the sequencer is doing this, and one region of the sequencer is doing that, and another thing is doing this, another thing is doing that, then like you can add stuff in there. A lot of stuff. I mean, it doesn't matter how much it is. It like, obviously like you want performance, but like the pattern of having, you could either have a dozen entry points to your Rust program, at which point you have a really complicated code base. I don't see any reason why doing that is better than just having one structure that Flutter will talk to. Everything Flutter needs, that structure handles, and then that structure handles all the internal complexity. Flutter needs to know nothing about the internal complexity. All it needs to know is how to create, how to destroy, and how to talk to that one structure. Inside that one structure, you initialize your MIDI library, you initialize your MIDI device, you initialize your MIDI input ports and output ports. Everything that you need to handle is in there. And that's the stuff that will talk to Java. That's the stuff. Oh, you probably in your sequencer, you also want to have Java context. Arc Java context, right? And then inside Java context, like abstract the details of the implementation details of how you do foreign function interfacing as soon as possible. Because your Flutter code will see your sequencer. It shouldn't need to know that your sequencer uses and talks to Java, and it shouldn't need to know that your sequencer opens a shared library in order to do its business. It should literally only need to know that there's a sequencer and that your sequencer has these routines that it can call, and that every time it wants to trigger one of those routines, it can just call it. Yeah, okay. I explained actually more than I explained in the previous video with this, because I showed how to handle the Flutter to Rust interface. So the overall diagram is Flutter talks to Rust, Rust deals with a shared object, Rust deals with Java. Flutter should probably need to know nothing about Java. The Rust codebase that you write, that should handle talking to Java, that should handle talking to the shared object. As long as the build system for the Rust project is correctly written, Flutter, if it's invoking the Rust build system, will get the benefit of that without you having to configure it from Flutter. Flutter itself, I don't know how Flutter's build system works, but it's like some variant of this. I hope this has been helpful. I hope I don't come across as too abrasive. I'm just trying to like remember everything that I said earlier so it can be helpful for you. This is interesting to me because like I know how these pieces work, but I don't have a ton of experience of Flutter or Android programming. I just know that like from what I've read, it's like basically this. I'm interested to see what you end up building here though. It sounds like an interesting project. I wish you luck with it and like stay in touch, definitely. Okay. I hope that was helpful, and yeah.